Hey guys, so today we're going to be talking about the Dijkstra's shortest path algorithm. And I know we already did it in class, but I'm just going to do like the min heap implementation of this algorithm, which saves like a little bit of time. And yeah, so let's get started. So first, let's just briefly look at the steps. So we're going to create a set S, which keeps tracks of all the vertices included in the shortest path tree. Like this algorithm, like the goal of this algorithm is to find the shortest path from one source vertex to everybody else in the graph. And here we're just gonna, keep track of like vertices that we already did. Like we already know, like we will find the shortest path. Okay, now we're gonna initialize a min heap of size v. This is the key step. And all the distance values are set infinite, except for the source index, it is valued 0 because we need to start from, we need to start expanding from that specific vertex. Yeah, so min heap of size v. And for step 3, well, S does not include all the vertices. Like we didn't finish looping through all the vertices. We need to first pop U. And in here, U has the minimum distance value because we have like a min heap. So of course, the first element we popped out, we have like the minimum smallest like distance value. We're gonna pop U and we're gonna append it to S. It means that we're done with like this specific vertex. But we also need to update the distance value of all the adjacent vertices of U, which means if there's an edge between U and this other vertex, we need to update the distance value following the rule below. So if the current distance of this specific node is larger than the, like we first go to U and then we like from U we go to V, like plus like the weight of like the edge of UV. If this is larger, then we're gonna update this like distance to this new distance we have here. But if it's like smaller, then we just keep the same thing in the min heap. And we're gonna repeat until we have like we find like a shortest path from the original vertex, the source vertex, to every node in the graph. Yeah. So let's look at an example if this is like not intuitive. Okay, so here's the picture. So we can see like this is like an directed graph. Like this algorithm would apply to directed graph too, but here we're just gonna use this example. And I'm gonna start like writing like the distance. So this is the min heap that we kept, which does not look like a min heap. Well, we'll do it. So for at the beginning, we initialize everything to infinity, and for 0, it will be 0 because 0 is like the source vertex. So obviously, this is the smallest, and we're gonna cross it out. And we're gonna see like for 0, 1, and 7 is the adjacent vertices. So here we have 4, and for 7 we have 8. Yeah, this is obviously smaller, so this is the first element we want to pop out. So when we get rid of it, we see that we can go to 7, we can go to 2. For 2, it would just be 8. 8 is smaller than infinity, plus 4. But for 7, it's kind of different. So we can do 4 plus 11, which is 15. But it's actually larger than 8, so we just keep 8 here. So this is actually smaller, so we're gonna cross out 7. From 7, we can go to 186, but 1 is already included in the, here we keep track of the vertices we already did, and we don't go there anymore. So we just go to 8. So for 8, that would be 8 plus 7, which is 15. And for 6, it would be 8 plus 1, which is 9 here. Yeah, and obviously now this is the first element we want to pop out. And from 6, we can go to 8 and 5. We don't go back anymore because 7 is included here, 6 is included here. And to go to 5, it's obviously going to be 9 plus 2, which is 11. And when we go to 6, when we go to 8, that will be 9 plus 6, which is 15. Same as this one, so we don't do any, update. Again, we pop 5 out, and yeah, so from 5, we can go to 2 and 4 and 3. So to go to 2, we can do 11 plus 4, and this is again, larger than 12, so we don't update it. And for 3 and 4, we do the updates. But yeah, so we just follow, the process, and we're gonna get the rest of the nodes. I'm just gonna stop here because I'm pretty sure you guys already get the clue of it. Okay, and the running time of this algorithm is E log V, mainly because it takes log V amount of time to decrease key. Like we need to keep the structure, the data structure, which is the min heap here. Like we need to make sure the element we pop always has the minimal distance compared to other nodes still in the heap. And obviously there's some drawback of this algorithm, but we already like mentioned it in class and we did like a lot of like things to make up for it. So I'm just gonna skip that here. But thank you for listening.